Alright, so this video is all about vectors in 2-space and 3-space. 2-space just means 2 dimensions, and 3-space is in 3 dimensions. Now what is a vector? If we look at vector A, we see that it is a line, so it has a magnitude. It has a length, so if it's 2 meters, this is 2 meters long, and it has a direction. This arrow, it represents that it's going somewhere specific. Now a scalar, on the other hand, would just be a line, so it would be 2 meters, not going anywhere particular. Now vectors can be represented as matrices, and their matrices look pretty simple. It's just a singular column. So here we have 2 values, and this means that it is in 2 dimensions. So x is 3 and y is 2. If I were to draw this, I just go 3 units to the right and 2 units up, and then draw a line from my origin to my end. I'll show you in the next slide. So here, if I were to draw the vector 6, 2, I go 6 to the right, 1, 2, 3, 4, 5, 6, and 2 up, 1, 2. Then I draw a line from where I started to where I ended. See, U here, it has a little arrow on top of it. That's just saying that it is, in fact, a vector. Now, just like with normal matrices, I can add vectors together. All that looks like is I have this vector plus this vector, and I take the first number plus this first number, so 6 plus 3 is 9, 2 plus -1 is 1. So if I were to draw this addition, I have U, and then I'm adding on V, so I draw a V at the end of U, which looks like this. And my resultant vector starts at the origin and ends at the end. And that is what I just calculated. Now we can also multiply vectors by a scalar. So here I have V, which is the blue vector, and it is 2, 3. So 2 to the right, 1, 2, and 3 up, 1, 2, 3. If I were to multiply it by 2, I just take every number and I multiply it by the scalar. So 2 by 2 is 4, 3 times 2 is 6. And look at the purple one. It is going in the exact same direction. I know it's like not super perfect, my line, but it's going in the exact same direction, and it's just twice as long. Now where this is all going is linear combinations with vectors. So the equation for linear combination is AV, where A is a scalar, V is a vector, plus B times W, where B is a scalar and W is a vector. This graph might look super complicated, but it's okay, I'll explain it. So here we have the black vector that's pointing to the right. If I were to multiply it by 2, I would just draw it twice as long. We just did that on the last slide. Now I could also do times -1, which would mean it would go in the negative direction. I could do times 1/2, which would make it half as big. Now let's say I have the blue vector, and I can do the same things to it. So let's say the vector V is the black one, and vector W is the blue one. If I were to add them together, I'm connecting the end of the one to the other one. So if here I have this vector plus this vector, I'm just drawing a line from them. Now I can do this forever, pretty much. So if I draw this twice as long and this is half as small and I add them together, I can keep doing that, and all my possible combinations is called the span. So for this example, the span is everywhere. It is literally everywhere on my graph. But let's imagine that the blue line does not exist and we just have the black line. Well, my span would just be one straight line, right? Because if I add this black line to this black line, well, it's still just a straight line. So my span wouldn't be the whole graph. Hopefully this makes a tiny bit of sense. We're going to go over a full example, and hopefully it makes more sense at the end. So the question here is U a linear combination of V plus W? So here I have U, and I want to know if this is possible. So if I go back here, I want to know if some random vector is a possibility for adding one vector to the other. Here I have u, v, and w. To do this, I'm just going to write it out like I had in the equation before. So I have u, vector u, is equal to a times vector v plus b times vector w. Now I want to know if this is possible, if any number at all of a and any number at all of b can possibly equal this. To do that, I'm going to apply my normal rules that I know, and hopefully you know too. So I have scalar multiplication, which means a times 1, a times negative 2, a times 2, same for b. I just rewrite it like this, so I have a negative 2a plus 2b, b, and b. I'm going to keep doing my normal rules. When I'm adding two vectors together, I just add the same rows. So I'm going to do that. Here I have a plus 2b, minus 2a plus b, and 2a plus b. I don't really want to be dealing with my a's and my b's in my matrix. I'm just going to take them out. And all I'm left with is an augmented matrix. So here are my answers, and here are my a's and my b's. I have 1, 2, negative 2, 1, 2, and 1. What I want to see is if this is possible. If you remember from a few videos back, if a matrix has no solutions, it means that this number is 0, this number is 0, but my result is not 0. So if I have like 0x plus 0y is equal to 10, that doesn't make sense. There are no solutions to it. So my answer is no, it's not a linear combination. But I need to figure that out. To do that, I'm just going to start with my normal augmented matrix. So I want my negative 2 to be a 0. I want this 2 to be a 0 as well, because this is already a 1, right? That's what we want. 1, 0, 0. I'm going to do these both at the same time. So my new row 2 is row 2 plus 2 row 1. Negative 2 plus 2 times 1 is 0. And my new row 3 is my old row 3 plus my old row 2. 2 plus negative 2 is 0. I write that out, and here's my new matrix. So I have 1, 2, negative 1, that didn't change. 0, 5, negative 1, 0, 2, 1. My last step is to turn this 2 into a 0, and then I'll see what happens. To do that, my new row 3 is my old row 3, minus 2 out of 5, row 2. So this becomes 0. And what I see is that this number here is not a 0, and that means that there are no solutions to this, and this is not a linear combination at all, so we cannot do this on our graph. Now the next video is going to be about the norm and the dot product, so we're just going to be continuing with vectors.